So today I'm going to talk about nuclear electric resonance and a means of controlling nuclear spin via this method. So we have a problem. We would like to control and detect a single nuclear spin in an atom. That could be, for example, phosphorus or antimony. But nuclear magnetic resonance is useful for large ensembles of spin, and use it in medicine and mining and chemistry, material science, just to name a few. But the magnetic fields cannot be localized. This is per the laws of physics, and the magnetic control of a single spin inevitably affects neighboring spins. As you can see in this picture A over here, you have this oscillating magnetic field B1, and the field naturally is just going to encircle the antenna, the magnetic antenna, and any spin in the vicinity of that magnetic field would be inevitably affected by the field itself and would orient it and affect its coherence. So previous attempts at using electric fields, because this is an emerging field, especially for physics and physics applications, and we'll get into that in a little bit. But they would use essentially electric fields to modulate electrons to transduce magnetic fields for nuclear resonance. This uses the hyperfine interaction between electrons and the nucleus. And essentially, from the nucleus's perspective, the motion of the electron and the transitions of the electron between energy levels is a magnetic field from the perspective of the nucleus, as we actually learned in this class. So this is sort of like inevitably still affects nearby neighboring spins because of this magnetic field that's being transduced by an electric field for the electron, but ultimately you want to change the nuclear spin, and so that's sort of going to affect it regardless. And then as you can see in B and C here, you have this is using the example of phosphorus, and those blue line transitions are the electron transitions, and the red arrows right there between the states are nuclear transitions. So you can use that to make the magnetic resonance easier using electric fields, but it's still not completely purely electric. So nuclear electric resonances comes into the picture in 1961. And essentially you use RF magnetic fields, which you can think of as a closed circuit antenna. Those are replaced with an RF electric field, which comes from an open circuit antenna. And your atom, which in this case, we're going to be talking about antimony, is going to have to be ionized in order to avoid this hyperfine modulation that could add those nuclear magnetic resonance effects, which is undesirable in multi-spin devices because you don't want to affect neighboring spins if you're trying to control a single spin. So then you strain the lattice, the lattice of the substrate, to create an electric field gradient that causes a splitting of the nuclear resonance frequencies, which is the Stark effect. This is basically an electric version of the Zeeman effect, which is what allows for nuclear magnetic resonance. So nuclear electric resonance has sort of its foundation in the other side of this of the coin, which is the Stark effect. And then you want to use RF electric oscillation to excite transitions between these levels, which you can then use to read out for the frequency of the resonant frequencies, and do your Fourier transform and all that. And then you want to add the electron back for readout via so you have, in order to actually read the states and whatnot, you have to use this hyperfine interaction, because you have to use this sort of like single electron transistor that can either read like a 1 or a 0 or something like that, based on whether or not the electron had a transition or something like that. So then you can see in this picture here, this is this picture to the left where it says SET donor gates, and the gap is actually from this paper that this whole talk is based on, from University of New South Wales. As you can see, they're using their microwave antenna was actually damaged. There's a gap in between where it was supposed to be a closed circuit, and this created an open circuit, which is essentially turns the magnetic antenna into an electric antenna. And they noticed that there were still some weird readings coming from the atom, which was in between those four blue those 4 blue electrodes. And once they noticed that it was actually a form of nuclear electric resonance, then they were able to actually use these donor gates, the blue lines, to start controlling the atom. And they realized that nuclear electric resonance was actually possible. And as you can see to the right, there's this Zeeman splitting, which is from the static magnetic field, which isn't oscillating or anything. And then there's a further quadrupole effect, which comes from the sort of electric Stark effect, you can think about it. And to the right of that, you can see that there's a picture of the colorful one, the rainbow one, sort of looks like you can see darker red is where the lattice strain is actually happening, shear strain. And this is what's resulting in this electric field gradient at the nucleus of this antimony atom. And below that, you can see the electric field graphically. So this is a really nice quote from the lead investigator. As you can see, performing magnetic resonance is like trying to move a particular ball on a billiard table by lifting and shaking the whole table. Whereas electric resonance is like being handed an actual billiard stick to hit the ball exactly where you want it. So if there's anything you take away from this talk, I think that's a really nice quote that sort of summarizes it all. But some disadvantages to nuclear electric resonance and some similarities to NMR is that nuclei must possess electric quadrupole moment, which essentially you can think of as like a ellipsoid-shaped nucleus with a slight imbalance of charge distribution, sort of potato-shaped. And nuclei must also have a spin greater than 1/2. So this is for heavy nuclei and heavier atoms. And the nuclear coherence can now be affected by magnetic and electric noise. So this means that the dephasing time between like the quantum state and just classical, where you lose that sort of quantum coherence, is shorter. And also nuclear electric resonance is a weaker effect than nuclear magnetic resonance, as the electric fields, of course, fall off rapidly beyond the tip of the electrode. That's just simple electromagnetic theory. And NMR and NER both rely on Zeeman splitting. As I said before, there's still a static magnetic field, but NER takes it a step further by using purely RF electric fields, and induce the sort of stark shift from that electric field gradient of the resonant frequencies, which is attributable to that lattice strain. So some applications that will ultimately result from this are in quantum computing, of course. So spins can act as qubits, quantum bits essentially, that can exist in a sort of superposition of being like up or down, and during coherence, of course. And they can be computed on, which allows for advances in search and factoring algorithms. So, instead of having to search through, like 100 different results individually, incrementally, you can sort of do searches simultaneously, which cuts down on computation time by orders of magnitude. Same with factoring. This is a huge threat to classical cryptography, as if you ever read about this sort of issue in the news and popular science. People are really worried about quantum computers being able to decipher, your encrypted internet traffic and passwords and whatnot. You also have quantum sensors, which NER, nuclear electric resonance capable nuclei, can sort of act as precise and electric and magnetic field sensors, due in part to this NMR and NER sensitivity combined. So this allows for just a further precision in sensing of these fields if you're doing physics experiments and whatnot, as opposed to having only magnetic sensitivity. Further, you can have mechanical strain and quantum chaos and spintronic devices, and the list goes on. But before I get to the last slide, which is questions, I would say this single paper, which comes from the University of New South Wales, is a really intriguing read if you're interested. Being a UT student means you have access through Nature magazine. So the experiment was sort of an anomaly. They were actually doing nuclear magnetic resonance, but like I said, they damaged their antenna because of a surge, electrical surge, and they ultimately had this happy accident in the lab that resulted in this sort of rediscovery of nuclear electric resonance, because it was sitting dormant for like decades because the experiment was really difficult. So just a good reason why we fund sort of fundamental research like this, because these sort of things can lead to happy accidents that now become the whole field of study. So questions?
Thank you. That was exactly 10 minutes. I get that is really fun and it's nice. It sounds like um, I feel like a lot of times when we write our research papers, we often just write what happened instead of how we got there. So it's nice. It seems like they explain in the paper how it was a happy accident.
Right.
We should do that more often. Um, any questions for Anthony?
Yeah, I had a quick question.
Go ahead.
So you mentioned, so in NMR, right, you apply like an RF magnetic field to flip the spin, but in nuclear electric resonance, so you're applying an RF electric field, and you mentioned that there needs to be the presence of like an electric quadrupole moment. So is it the polarization, like the quadrupole moment that's flipping, or is it also the spin that's flipping in this case? I guess I was a little confused on that.
So I believe the RF electric field is to induce these transitions between the states that are coming from the splitting of the Zeeman from the Zeeman effect of the, so you have both NMR and NER use the static magnetic field. It's not oscillating, just to induce this splitting of the energy levels. So I believe the quadrupole moment is actually what I mean, you're affecting nuclear spin at the end of the day, but it does also come from sort of, it's attributable to that nuclear quadrupole moment. But I think the quadrupole moment is ultimately there for there's a electric field gradient, like I said, from the strain of the lattice. So in this case, the strain was coming from they deposited aluminum gates, which have a different like thermal contraction than the silicon substrate. So that resulted in the lattice strain on the around the nucleus, and that gave you that electric field gradient. So I think that's what the quadrupole moment was referring to, is that because it had a quadrupole moment, this electric field gradient allowed it to sort of allow the nucleus to reorient itself because of these oscillating RF electric fields. So it's still affecting nuclear spin, but the quadrupole moment is a part of the story because of the gradient in the electric field from the strain of the lattice. And they used, they implanted the ion, using ion implantation to put the antimony atom in there. So typical fabrication techniques has a lot of relevance to, a lot of that's nanofabrication stuff.